Hi there. In this video, we're going to talk about the Dirac-Delta function, also called the impulse function. So it's a very important function with a lot of different applications and it's used in many places. It can represent, for example, a sudden large force that acts on something for some period of time. If we also think about a mechanical blow that just happens instantaneously, if we also think about a surge of voltage through a current, all of that can be modeled by the Dirac-Delta function. So we start the analysis by considering just a pulse. So this pulse you see in this first graph, we have time and some function of time. And this pulse has a certain length b. So we want to consider the area of this pulse, and we want the area to be 1 unit. And of course, area is equal to length times height. So if this length is b, then it must mean that this height is 1 over b, because b times 1 over b gives us 1. So now we consider what happens if we take this pulse and we halve this length. So we take this length and we divide it by 2. So that's what we're considering in this second graph. We have time and a function of time, and now this length of this pulse is b over 2. So that means that this height must be 2 over b, because again, we want this area to be 1 unit. And if this length is b over 2, then the height has to be 2 over b such that is equal to 1. So we consider now reducing this length b to be as small as possible, such that we now consider where b approaches 0. b is so small that it's just approaching 0. It's literally almost 0. So in that case, we still want the area to be 1 unit. We have time and we have a function of time. So what we have to consider is this length approaching 0, okay? That means that this height must approach 1 over 0. And 1 over 0, as you know, is infinity. So what this means is that this function has this value of infinity if we start considering b approaching 0, because 0 times 1 over 0, and this 1 over 0 is approaching infinity. So this is the Dirac-Delta function. This is the unit pulse we're talking about. This b we can't show as a value of 0, so we just show it as a line, and this arrow represents the fact that it's going to infinity. So the way it's written as delta. That's why it's called the Dirac-Delta function. And it's written as t minus a. And this a is the value of t at which this unit pulse occurs. We can say that f of t is equal to delta of t minus a. And if a is equal to 0, it just means that this pulse occurs at the origin. So just to remind once more what this thing actually is, it's just a unit pulse, and its length is approaching 0. That means that its height is approaching infinity, such that the area is equal to 1 unit. And since it is the case, we write it as delta to show that it's a function of t minus a, and this a is the time at which this pulse actually occurs. So since we've said this area is equal to 1 unit, we can write it to be the same as the integral. We can say that the integral of this Dirac-Delta function, t minus a, and if we consider it to be between 2 points, so there's p and there's q. So this p and q just means that it's happening in between. This impulse a is between p and q. So we can say that a is between p and q. So if we integrate between p and q, then it means that this integral is going to equal to 1. What we're saying is that outside of this Dirac-Delta function, outside of this pulse, this function takes on the value 0. So we can say that between a, so how we'll write it is that we'll say that this Dirac-Delta function of t minus a, it's equal to infinity when t is equal to a, and it's equal to 0 everywhere else, so when t is not equal to a. So if this unit pulse is equal to 1, the area simply at a, it just means that if between P and A it's going to be 0, and between A and Q it's going to be 0, and at A itself it's going to be 1. That's what the integral is. So we can consider now if we take this Dirac-Delta function and multiply it by a function. So we have this integral between P and Q, and we have a function of t, and we multiply it by the Dirac-Delta function. So what is this integral going to be? So let's understand what's happening here. So this Dirac-Delta function, as we had just written, it's equal to 0 everywhere else where it's not equal to a, where t is not equal to a. So if we're just considering one single fixed value of t, that's at a, it means that this function of t just has that single value at this particular point. So this function would take on a single value at this point a. So we can rewrite this integral as being integral from p to q f at a times delta t minus a. So we have just said that this function takes on just a single value f at a when t is equal to a. So what this means is that f of a is just a constant. We can take it out of this integral and take it out of this constant, take it out of the integral. We can say that this is equal to f of a times this integral from p to q of delta t minus a dt. And what this is just going to equal to, since this integral is equal to 1, which we have just seen, it's just going to equal to f of a. So if, as an illustration, we're taking the integral from 1 to 3 of some function, t squared plus 4, and we're multiplying it by the Dirac-Delta function, delta into t minus 2 dt. So what we're saying is that this pulse occurs when t is equal to 2. So this is just equal to then this function at 2, which is just substituting 2 inside t squared plus 4. So we have 2 squared plus 4, which is just equal to 8. So it's as simple as that. And then lastly, we can actually now consider the Laplace transform of the Dirac-Delta function. So the Laplace transform of the Dirac-Delta function. What is it going to be? Well, we can use this analysis that we've just used. We can take the integral from 0 to infinity using the definition of the Laplace transform, which is the function that we're considering, which is the Dirac-Delta function, times e to the minus st dt. And what have we seen? We have seen that it's just equal to the function at that certain given point. We can think of this 0 as being our p and this infinity as being the q. So there's a here. So just this is 0, p is 0, and q is infinity, and we have it in between. So we can think of this e to the minus st as being this function which we have now multiplied by the Dirac-Delta function. In this case, we have shown that it's just the function at a. Okay? So in this case, it's just e to the minus as. So that's what the Laplace transform of the Dirac-Delta function is. So we can generalize this even more. What happens if we now take the Laplace transform of some function of t multiplied by the Dirac-Delta function? We perform the analysis in the exact same way. We're using the definition of the Laplace transform. We have the integral from 0 to infinity, and then we have f of t times the Dirac-Delta function times e to the minus st. So the exact same logic applies. Instead of just having e to the minus st, we can consider f of t and e to the minus st to just be a single entity forming the one function. And in the case here, it will just be that this entire integral will just become f of a times e to the minus as. So just a basic example illustrating this, we can have the Laplace transform of sine 3t times Dirac-Delta function of t minus pi over 2. So this is just equal to f of a times e to the minus as. So in this case here, it's just going to be sine of 3 times pi over 2, because a is pi over 2, 3 times pi over 2 times e to the minus pi over 2s. So sine of 3 pi over 2 is just minus 1. So we're going to have minus e to the minus pi over 2s. So that's our final answer. So this video has given an illustration of the Dirac-Delta function, what it is, how it's defined, how it's used. We see that it's just a pulse that's occurring at time a, and the area of this pulse is 1. So we have written this as the integral of this pulse at a is equal to 1. And then we have shown that when we multiply it by a function, since it's just one single point at a, it means that this integral is equal to that function at that given point. And then if we now extend this to the Laplace transform, we have seen that the Laplace transform of the Dirac-Delta function is just e to the minus as. And then if we multiply it by a function and take the Laplace transform of it, it's just that function at that value times e to the minus as, which we then demonstrated with a simple example. So thank you very much for watching.